All right, let's go ahead and get started. So here's the start of a bold claim. All software should be, so is there a word we can use here that we can all agree on? Well, probably not, but I'm going to try anyway. How about fast? All software should be fast. Okay, but fast is a subjective thing. So let me try and quantify what I mean when I say fast. In simple terms, I'm defining fast to mean that the software should respond to user interactions immediately, or at least the perception of the user should be a near instantaneous response by the software. Now, to better quantify this, most people agree that if your software responds within 100 milliseconds, to us humans, that feels instantaneous, but 100 milliseconds isn't a whole lot of time to start with, right? I mean, if your application is blazing fast, it still might be hard to achieve that 100 millisecond goal just because we're limited by the speed of light. For example, here's a table that measures how fast data can travel from one location to another. Essentially, these are real ping times. And as you can see here, many of these locations take longer than 100 milliseconds just in transit time. So this is what I'm getting at when I say our applications are limited by the speed of light. Essentially, the speed of cloud-based applications is limited by the distance the data has to travel. And of course, data can at max travel at the speed of light. In other words, the speed of light can be a limiting factor in how fast or responsive our applications feel. Okay, so how do we overcome this speed of light limitation? Well, obviously, something like this, where your servers and your users are separated by long distances, isn't going to cut it. We've got to somehow get our applications and its data physically closer to your users. Okay, so how do we get your application and data physically closer to your users? Well, some of you might be thinking that edge computing is the answer. Okay, but what does edge computing even mean? Well, if you talk to cloud service providers, they may tell you that edge computing is getting your servers physically closer to your users, which is valuable and does minimize latency, but it doesn't eliminate latency, it just reduces it. And it's not what I mean when I say edge computing. When I talk about edge computing, I'm not talking about data centers or servers. I'm talking about putting your application and its data literally at the edge. In other words, on laptops or desktops or IoT devices or other smart devices. And by doing this, we're not just minimizing communication-related latency, we're eliminating it completely. Well, with a few caveats that you'll see later in this session. Now, some of you are probably saying to yourself, aren't you just describing local applications, which we've had for decades? Okay, to be clear, I'm not talking about local applications. I'm talking about local first applications, which are significantly different, and I'll explain how they're different in a moment here. Okay, I know one of our collective goals should be to create fast software, but today's reality is that we're all used to slow software. In fact, we may be desensitized or numb to the pain of using slow software because it's normal. It's what we've come to expect. Now, some of you might be a bit skeptical of me saying software is slow and we're used to it, but I think I can make a pretty good argument that this is largely true with one picture. We all know what this means, right? It's an animated spinner, and when we see it, it means the software is doing something and it's going slow. You have to sit tight and wait for it to complete. You know, the fact that we all know what the spinner is, well, I think it's evidence that we're all conditioned to wait on slow software, but it doesn't have to be like this. Spinners can and should be something that we strive to remove from our software. And I believe in the next few years, user expectations are going to start shifting. What I mean is, most users see spinners and they don't question them today. In their minds, this is just how computers work. But as more and more applications eliminate spinners, user expectations are going to change, and they aren't going to be as tolerant of slow applications. And why should they be? Now, to be clear, there are legitimate reasons for software taking a bit of time, but I suspect that most of the time when we see spinners, the software isn't doing some sort of legitimate, expensive operation. It's usually just waiting on simple queries to finish and returning that query data to the client. In other words, we see spinners mostly because of I/O-related latency. So how do we get rid of spinners? Or put another way, how do we write faster, more responsive software? Well, obviously, you've got to get rid of the slow stuff. And as I mentioned a moment ago, one of the slowest things our applications do is I/O, or input output. And of the different kinds of I/O, talking across a network is one of the slowest things your apps can do. Okay, so how slow is network I/O versus other types of I/O? Well, there's a good chance you've seen this reference before. It's a list of latency numbers for various types of I/O, and at the bottom of this list is the amount of time it takes to send a single packet to another continent and back. So network I/O, as you see here, is orders of magnitude slower than most other types of I/O. All right, so these numbers are helpful, but to truly appreciate the pain of slow network I/O, I think you need to experience it. So I created a visual example that I want to show you right now. So I made a simple contacts application that I made two of them and they look nearly identical, but I implemented them in two different ways. The version of the application on the left is a conventional client server application, and I'm saving the contacts in a Postgres database in AWS. Now, this other version of the application on the right is almost identical to the application on the left, but it's written as a local-first application. Now, I haven't exactly told you what a local-first application is yet, but we're going to talk about what they are, how they work, and so on in a moment. But first, I want to give you a few reasons why you should even be interested in local-first applications. So I prepared a quick side-by-side video of these two apps to capture the user experience of just navigating to each contact. I've also got timers on each app just to quantify how fast we're able to navigate each list. So I'll go ahead and play this video, which is about 8 seconds long, and I'll pause for a moment so you can watch. Okay, so the Localfirst app on the right took 3.3 seconds, and the conventional client-server app took 7.4 seconds. So in practice, the Localfirst app was over twice as fast. Now, I know this demo is artificial and that users wouldn't normally race through every contact in their list, but what you should keep in mind is every single action performed in the client-server app is going to be noticeably slower in the best of circumstances. And this slowness is even worse under poor conditions. For example, I did the exact same exercise again, but this time I throttled the network to simulate slower 3G connections. And check this out. The client-server app on the left is painfully slow, and the Localfirst app on the right is just as fast as before. Now, maybe some of you are thinking, small amounts of latency like we just saw is fine. Okay, I don't really understand that mindset, but maybe you've got your reasons. So let me give you another argument for considering local-first applications, which is the fact that local-first apps not only work well when the network is bad, it continues to work when there's no network connection at all. In other words, it works in offline mode as well. We'll actually play with this offline mode in a few minutes here. Okay, so how is the Localfirst app so much faster than the client-server version? Well, based on the hints from earlier, you probably know the reason. It's because the Localfirst app has all the data it needs available locally, so it doesn't need to talk to a remote server to fetch the contact data. All right, you might be thinking, sure, the Localfirst app is faster than the client-server app, but what are the trade-offs here? I mean, do we lose a bunch of features and benefits in this Localfirst application when compared to the traditional client-server cloud-based solution? Well, I want to make a clear distinction between Localfirst applications and local applications, because as I said earlier, there's a significant difference between these two types of applications. Local applications have existed since the PC came out decades ago, and as developers, we rely heavily on local applications because they're really fast, and for the most part, they don't slow us down. And the reason for that is because the local application obviously has the data it needs co-located with the executable. In other words, there's no need for slow network I/O. But local applications don't have all the features and benefits of client-server-based applications, right? For example, client-server applications can have multiple users that can collaborate on common tasks, often in near real time, and these features are typically not available in local applications. But Localfirst applications are really an interesting hybrid between local applications and client-server applications, at least in terms of features and benefits. You'll see what I mean by this in a moment here. Okay, so what exactly is a local first application? Well, it's an application where the source data isn't on a server, it's actually co-located with the application on the computing device. So everything is really fast because you're not waiting on slow network communication with cloud-based servers. Okay, again, this kind of sounds like a local application, right? So what's different with the local first application as compared to a local application? Well, here's an interesting aspect of local first applications, which is different from traditional local applications. When you're using local first technologies, you can add a network adapter here, which connects to your local data, and then any updates you make to that local data can be replicated to other computers in near real time without conflict. So for example, with the contacts application we saw earlier, anytime you add, update, or delete contacts, those changes in the contacts can get replicated to other computers in near real time without conflict. And the replication happens automatically. In other words, you, the developer, just needs to modify the local application data, and you don't have to worry about replication because it's handled for you. So what are these other computers on the left and right? Well, they're peers, and it could be some other person on a laptop or a smartphone or even another server. But try not to think of this as a traditional client server setup. It's really just a peer-to-peer connection that happens to be with the server. So essentially, with a local first application, you get all the speed of a local application because remember, your data is really just using, so your app is really just using local data, but you also get many of the features and benefits you'd expect from cloud-based or client-server-based solutions. For example, in a client-server system, you can create multi-user applications that can collaborate on common tasks and support near real-time features. And guess what? You can do the same type of things with local first applications. And additionally, you can do the things with local first, like offline mode, which isn't well supported in client-server-based systems. Now, looking at this slide, you might think, why would you ever create anything but a local first application? Well, to be clear, there are many use cases that wouldn't work well as a local first application. And there's definitely limitations on local first applications that you need to be aware of. And in a bit here, I'll talk about some good use cases and limitations of local first. But local first does offer an intriguing set of features. And keep in mind, there's no reason you couldn't mix local first with client server where it makes sense. Okay, I want to go through a quick thought exercise that I think will help make the case that local first allows you to build apps with similar features to client server apps. Take, for instance, a Kanban board like Trello. Now, most seasoned developers have a sense of how to create a client server-based Kanban board. It would probably involve a WebSocket connected to a server, and all updates would get sent to the server over this WebSocket connection. And then the update could potentially be sent to other clients, providing near real-time updates. Now, you could build the same Kanban board application as a local first application. And when updates are made locally, the updates can be replicated to other peers, either directly or through a relay, which effectively provides near real-time updates that are possibly faster than a client-server solution because it's using efficient peer-to-peer communication. And there's a subtle but noteworthy benefit in the local first Kanban app, which is the fact that the programmer doesn't really have to think about any kind of network communication. As a local first developer, you just modify the local data and the network updates are automatically propagated and merged to the other peers without conflict, which is kind of nice because you've got less things to think about and deal with. So in a way, with local first apps, you're getting the best of both worlds. The application is as fast as a local application, but you also get the real-time collaborative features you'd expect from an application like this. And also, this local first application works offline and online. So for example, if the app goes offline, you could still add, edit, or delete Kanban items. And then when the network connection is restored, the work you did offline will be automatically synchronized with other peers. And by the way, offline mode is a feature that Trello and most other client-server Kanban boards don't have. We're going to play with this offline behavior in a few minutes, and you'll get to see how seamless it works. Now, many of you are probably wondering how this data synchronization works, and you might also be wondering what happens if there's a problem with synchronization. Okay, so let's dive into this synchronization data a bit. Let me ask you this. How easy or hard do you imagine it would be to write the code to handle data synchronization between multiple peers? Well, if you've ever tried something like this, you know it's pretty tough to get right. In fact, it's so challenging that almost nobody does it. Well, that is until recently. So data synchronization is hard, but here's the thing. You don't have to worry about writing synchronization code in Localfirst apps because there are libraries to handle it for you, such as the mycelial library, which we'll look at in a bit. But to be totally transparent with you, we wouldn't be able to write this synchronization code, but for a relatively new technology called conflict-free replicated data types, or CRDTs. In fact, CRDTs are essentially the breakthrough technology that makes these local-first applications even possible. They're kind of a big deal in my opinion. Okay, so what exactly are CRDTs? Well, there are special data types that are essentially shareable data types. What I mean is, CRDTs are designed in such a way that you can easily share data from one node to another in a conflict-free way. In other words, any local updates you make can be sent to other computers and merged into their replica without conflict. So how do CRDTs work? Well, to fully understand how CRDTs work, you have to understand order theory, and in particular, join semilattices. So let's put on our math hats and let's dive into some order theory. Does that sound good to you guys? Okay, I'm just kidding. Don't leave. This isn't a math class. We're not going to dive into order theory, but I mentioned this for a reason. And the reason I bring this up is because if you're new to CRDTs, you might be a bit skeptical of the technology. But what you should know is there are mathematical proofs that show the correctness of CRDTs, and that should give you confidence in the technology. Okay, but I still want you to gain a comfort level with CRDTs, even though we're not going to dive into the proofs. In other words, I want you to have a practical working knowledge of CRDTs, so let's dive a bit deeper. So CRDTs are really a combination of the data you're interested in, the application data, plus some additional metadata. So what's the metadata for? Well, it's the data necessary to ensure that your replicated data can be merged with other peers without conflict. Okay, this might seem a bit fuzzy at first, but we're going to walk through an example in a moment, which should help you get a better grasp on what the metadata is, how it works, and why we need it. Now, again, I want to emphasize that you don't really need to know how CRDTs work to use them. You can just use a CRDT library, like the mycelial library, and all the complexity is handled by the library authors. But if you're new to CRDTs, you're probably still curious how they work. And so I want to give you an example of how they work by looking at one of the simpler CRDTs, the counter. Okay, let me set up a quick scenario. Imagine we're writing a simple app that counts people entering a music venue. Now, imagine the app looks something like this. It's going to be used concurrently by 30 people at various entrances to the venue. Okay, so you could write this counter as a typical client-server app, where every time you increment the count, a new message gets sent to a central server, and a response is returned to the client. But do you see any potential problems with this? Well, what if the network connection is bad, which is often the case at a crowded venue? Well, then the venue staff may start seeing spinners while they're waiting on a response to the server, and they may get timeout errors if the server doesn't respond in a timely manner. So talking to this server can be a real bottleneck in this otherwise simple process. Let's think about how this collaborative counting application might work as a Localfirst app, which of course would allow us to avoid the dreaded spinner and keep the flow of people moving along. So let's think about creating this simple counter app as a Localfirst app, but first we'll consider using primitive data types instead of CRDTs, just to see if a familiar conventional data type would work with this kind of a collaborative counting application. All right, spoiler alert, using primitive data types isn't going to work, which you probably could have guessed, and you'll see why in just a moment here. Okay, so let's say the data model for the counter app is just a simple integer. So now someone increments the count on the left, And then a moment later, the updated count gets replicated to the other devices, and everything seems okay so far. Next, we'll say the middle counter is incremented from 1 to 2, and at about the same moment, the other device increments its count from 1 to 2 as well. Okay, so now the middle device replicates its count to the first device, and the 1 becomes 2. And then a moment later, the device on the right replicates its count, and the 2 becomes 2. Okay, that's not correct. We know the count should be 3, right? Okay, so this simple example demonstrates one of the reasons that primitive types won't work for local first applications. However, if we swap out our integer-based counter with the CRDT counter, we won't experience the problem you just saw. And to increment the counter, all you need to do is call increment. And basically, this is all you need to know as a developer to interact with the CRDT counter. But even though you don't need to know more than what you see here, you're probably curious how they work. So let's look at how this counter CRDT might be implemented. So as a learning exercise, I'll talk you through one implementation of the CRDT counter. Now, obviously, a counter represents a number, but that doesn't mean the underlying data model has to be a number. Here's what I mean. What if our data model for the counter was composed of two things, a unique ID for each replica and a map? Then when the count is incremented, a key value pair is added to our map, where the key is the unique replica ID, and the value is the incremented count for this replica. Now, to get the actual count value, we just need to sum the values in the count map, which at this point is just 1. Then to replicate the data, we just send the entire map to the other nodes and merge the maps in a special way. And at this point, we've achieved consistency across the nodes. In other words, every node, or smartphone in this case, has the same count value. Next, let's walk through the problematic scenario we saw a moment ago with concurrent updates. So let's say both of these counters on the right get incremented at about the same time. Then each node adds a new key value pair to their count maps, where the key is the unique replica ID and the value is the count for the corresponding replica. So the first time the increment is called, the values will be 1. Then to calculate the current counter's value, we simply sum the map's value, which totals 2 for now. Next, the updated values get sent to the other replicas and merged into their local maps. And as you can see, the count value for each node is now consistent at 3, which is the correct count. Now, any subsequent increments will simply increment the appropriate partial count value in the map. So incrementing on this device will increment this key value pair, and incrementing on this device will increment this key value pair. And lastly, incrementing on this device will increment this key value pair. Okay, excuse me. Okay, there's more to know about a CRDT counter and how it works, but hopefully this small exercise gives you a sense of how they're implemented. You remember a few minutes ago when I mentioned that CRDTs contain the application data and also metadata? Well, now you see what I mean by metadata. The counter needs to store extra data in the form of the replica ID and the map, and the values of the counter is derived from that metadata. But again, I'll ask, what's the point of the metadata? I mean, why is it needed? Now, you may intuitively know what the metadata is for, and I did provide a high-level answer for this a moment ago, but I want to get specific. The metadata is needed so that the data types have all the information they need so that changes can be replicated and merged amongst peers in a conflict-free way. So in summary, the metadata is all about allowing updates to be replicated and merged without conflict. Now, a consequence of having to store this metadata is the fact that CRDTs require more memory than their conventional counterparts. So there are trade-offs when using CRDTs, and additional memory usage is an example of one of those trade-offs. And keep in mind, some data types use more metadata than others. But in recent years, researchers have figured out how to minimize and optimize how much metadata is needed to the point where CRDTs are now a viable technology for many scenarios. Another trade-off is the consistency model with CRDTs. In particular, there are periods of time when replicas can have different values. For example, when we incremented one of the counters a moment ago, the other counters had different values until the updates arrived at the other nodes. So CRDTs offer high availability and strong eventual consistency, the key word there being eventual consistency. Now, one of the next questions you probably have is, how do the peers in a CRDT-based system communicate? In other words, what sort of networking protocols are used? Well, CRDTs are somewhat network agnostic, meaning you have many choices and you get to decide how to connect the peers. So you could use WebSockets and PubSub to propagate the updates, or you could use server-sent events, or you could use WebRTC, or you could use a mesh network like libp2p, or some other gossip protocol. The next question you may have is, how do you ensure updates get propagated to the peers as appropriate? Well, there are some inherent properties of CRDTs that make updating peers a bit easier and more forgiving. Let me explain. There are three important update-related attributes of all CRDTs that goes back to order theory, and in particular, join semi-lattices from which state-based CRDTs are based upon. First, updates are idempotent, meaning an update from one peer to another can be applied multiple times and the result is the same effect. Let me demonstrate what I mean by idempotent. Let's say one of these counters gets incremented, updating its local count to 1, and then the updates are sent to other devices. And for discussion's sake, let's say the device on the left, maybe it got temporarily disconnected and it's not sure if the other devices received its latest update. So the device on the left goes ahead and sends the update again, and the update can get and that same update can get sent multiple times, and the result of merging the update multiple times gives you the same result. It's an idempotent operation. The next important attribute of all CRDTs is that they're commutative. Commutativity means changing the order of operands doesn't change the result. So for example, commutative means operating on X and then Y gives you the same result as operating on Y and then X. In other words, the ordering doesn't matter. The third important attribute of all CRDTs is that they're associative. Associativity means rearranging the parentheses in an expression will not change the result. So the result of this set of operations is the same as this set of operations. In other words, the order doesn't matter. Okay, so what do these last two attributes give us? Well, if you think of X, Y, and Z as replica updates, and you think of these operators as data merges, you realize that updates from one peer to another don't have to be propagated in any particular order. As long as a peer eventually receives all the updates in any particular sequence, the peer's state will become consistent with the other peers. Okay, given these properties of CRDTs, you can see that propagating updates between peers is easier and more forgiving than you might imagine, because updates can be passed to peers multiple times without any adverse consequences, and the updates can be passed in any particular sequence, and eventually each peer will converge on the same value. I want to circle back to this example for a moment. So is this a perfect solution for counting and limiting people, the number of people who enter a venue? Well, no, it's not perfect. For example, if you're trying to limit the capacity to some maximum number of people, well, if you aren't careful and you don't design the system properly, you might overshoot it because of the small delays in update propagation. It boils down to this. Is this a trade-off you're willing to make? This is one of the core questions you have to ask yourself when using a system that favors availability and strong eventual consistency versus a system that favors consistency over availability. I believe this is a worthwhile trade-off for many scenarios, but at times it will require creative, practical solutions to work around the trade-offs. And obviously there are plenty of scenarios where you'd pick consistency over availability. Let's take a look at an actual Localfirst app that I built, which is the simple contacts app you saw in the video earlier. And I'm going to go ahead and paste the link in the chat. So give me a moment to paste that link. And one more second to change my screen sharing. Now, this contact app probably doesn't seem special at first glance, but there are a few subtle things about this app which are interesting and I want to draw your attention to. First of all, this application is built with Localfirst technologies. In other words, all the data I'm using in this app is local data. And if you use the app, you can tell because it's really fast and you won't see any spinners. But just because our app is local first doesn't mean you have to sacrifice all the features and benefits you're used to in a client server-based application. For example, I've got two instances of this app open, which you see here side by side. And I'll go ahead and add a new contact in one of the windows. Now, as soon as I click save, you should see this contact get replicated to the other window. And sure enough, there it is. Now, if you have this app open as well, you should see these updates in real time as well. Now, I'm going to go ahead and pause for a second and give myself a chance to catch my breath. And I want you guys to have an opportunity to go ahead and add a new contact using dummy data. And if it works, you should see your contacts show up on my screen almost immediately after you add them. So I'll go ahead and pause for a second. All right, there's Jared. Do you see this toggle in the bottom left part of the screen right here? Go ahead and click it so it's in the off position. And when you do, it's going to disconnect the network adapter that I've referred to a few times. So with the application disconnected, can you still use it? Well, you can, because as I said earlier, Localfirst applications work offline as well. In fact, I'll go ahead and add a new contact and I'll delete another contact while offline. And I'll go ahead and delete a contact. And as soon as I toggle this toggle back to on, the changes that I made on the left should be immediately propagated to the client on the right, as well as your computer as well. And as you can see, Tina Fey is gone, and Jane Doe is on both windows now. Let me ask a question. What's the source of truth in this application? What I mean is, in a traditional client-server application, the source of truth would be the server, but what's the source of truth in this app? Okay, that was kind of a trick question. There is no single source of truth in this application, and there's a name for this kind of an app. It's called a local-first, decentralized, distributed application. It's local-first because all the data the app needs is stored and mutated locally. It's decentralized because there is no central server that we're relying on. And it's distributed because it resides on many computers like your computer and my computer. You know, I want to point out something subtle but important, which is the fact that the applications you build with these new technologies are inherently collaborative in nature. So for example, the counter app I talked about earlier, well, it's really a collaborative counting app. And this contacts app is really a collaborative contacts app. My point here is with these new technologies, you can build software where people collaborate on common tasks, or maybe people aren't involved at all. And you've got semi-autonomous machines that are collaborating on a common task. Give me a moment here and I'm going to switch my screen sharing and I'll show you an example of machines collaborating. For example, maybe our application is running on some sort of scanners that collaboratively count things that pass by them on a conveyor belt. This is a simple example of machines collaborating using Localfirst technologies. I want to reemphasize something I said earlier, which is the fact that CRDTs are a relatively new technology. I mean, they really haven't been a viable option until recently. And as a result, there aren't any full-featured CRDT libraries to pick from yet, but we're doing our part to change that. Additionally, at Mycelial, I think we've got a bit of a different vision than the other up-and-coming CRDT libraries. What I mean is, most CRDT libraries today seem to be heavily focused on text editing, you know, Google Docs style collaborative text editing. Now, CRDTs for collaborative text editing is interesting and cool, but we're focused in a different direction. We're focused on creating libraries that help you build full-fledged local applications. Okay, but what does this mean? Well, for example, our product roadmap includes things like schemas and data validations, time traveling, authorization, authentication, various network adapters, plus local and cloud-based persistence. In other words, we aren't focused on one aspect of CRDTs. We're taking a more holistic approach to fully supporting building local-first applications. Essentially, we're building open source tools with a unified vision around local-first development, and eventually we'll offer support services that frankly isn't available from anybody right now. All right, I want to talk about potential use cases of CRDTs in broad strokes. In other words, let's take a 30,000-foot view of CRDTs and their potential use cases. So the first category of use cases is computation in delay-tolerant networks. Okay, but what does this mean? Well, examples of delay-tolerant networks are systems that lack continuous network activity. So things like mobile devices, or maybe ships and submarines, or remote terrestrial environments, or even networking in outer space. And these are good use cases because CRDTs work seamlessly when transitioning from online to offline and back again. You know, peer-to-peer computing, in theory, is a very efficient model of computing, but it's never really taken off in the mainstream because we haven't had all the tools necessary to make it viable. For example, in a peer-to-peer network, it's common for peers to come and go, and you need to be able to handle this kind of churn, and CRDTs work well here because with CRDTs, it's relatively easy and efficient to bring a peer back up to date when they've gone offline and come back online. The next potential use case is data aggregation. So for example, consider video streaming services like Netflix or YouTube that have massive distributed content delivery networks. So in this kind of environment, how would you do something as simple as counting video views or likes? Well, what about the collaborative counter we talked about earlier? This would work pretty well, right? Okay, next is partition-tolerant cloud computing. This is essentially favoring availability over consistency in a partition, which is exactly what CRDTs do. And of course, CRDTs have the added benefit of offering strong eventual consistency. A couple of additional potential use cases are latency tolerance in wide area networks and disconnected operations or offline mode. Okay, these broad descriptions are fine, but here's something I'll challenge you with. Over the next few days or even weeks, try to keep local first and CRDTs in mind as you're using whatever applications you use day in and day out, and ask yourself, could this app take advantage of CRDTs? Personally, I've been looking at applications that I use through a CRDT lens, and I see lots of opportunities to use and benefit from CRDTs in a surprisingly large number of applications. For example, just think about the apps you use that need to synchronize data with other devices. This would be apps like the Kindle app, which keeps track of which page you're on in a book and synchronizes it to other devices, and it even synchronizes it to other applications altogether, like Audible. Another example would be reminder apps and calendar apps and note-taking apps and video streaming apps and password managers and diet tracking apps, and the list goes on and on. All of these apps have to synchronize data with multiple other devices in the cloud, and CRDTs could offer easier and more efficient implementations than the current solutions do. Okay, I don't want to make local first seem like a magical solution to all your problems, because it's not. And there's some considerations that are unique to local first applications, and I want to highlight a few of the important ones right now. So here's a scenario I want you to consider. Imagine that you and I are using the contacts app that we played with earlier, and both of us are offline. Then you make an update to a contact, changing the name, and then at about the same time, I delete the same contact. And now the question is, what happens to this contact when we both come back online? Is it updated? Is it deleted? Well, if it's deleted, then you might be puzzled and wondering what happened to the contact that you just updated, right? Now, this seems like a conflict, right? but the first letter of CRDTs stands for conflict-free. So am I lying to you? Well, this kind of a scenario is an example of a common misconception about CRDTs, especially to newbies. The problem here is when I say conflict-free, it doesn't mean what a lot of people assume it to mean. Okay, so what exactly does conflict-free mean? Well, what it means is the updates you made and the updates I made are guaranteed to merge in all replicas, and all replicas will converge on the same value. In other words, an update won't error out and won't be rejected by other replicas. The system will continue to function and move forward or progress without any sort of manual intervention. But conflict-free doesn't mean you're free of semantic conflicts in applications like the scenario that I just laid out. I mean, if you think about it, there is no magical solution to this kind of a problem. And by the way, the same kind of semantic conflicts can occur in client-server applications. So what can you do to deal with this type of conflict? Well, if this scenario is a problem for you, you likely need to create data structures that can better handle the semantic conflict. So maybe that means designing the contacts app to only support archiving of contacts instead of deleting. At least then, if a contact went missing, you could check to see if the contact was archived, which would help you make sense out of what happened. And then, of course, you could unarchive it if you wanted to. Now, as a quick aside, I mentioned earlier that we're building time traveling into our CRDT library, which can be a helpful tool for dealing with semantic conflicts because you can programmatically step through changes that happen over time and expose them to your users. The next thing I want to consider is the size of your data set. And if it's extremely large, it might be problematic depending on your implementation. So what do I mean by this? Well, if Localfirst data set grows to a substantial size, and then a brand new instance of the apps is created, then you're left with the challenge of having to ship the entire data set to the new instance, which might not be practical. Okay, if your Localfirst application is in the browser, then you've got to figure out how to persist that data in a safe way because browser storage shouldn't be considered truly persistent. So you'll likely need to synchronize your data with the cloud for persistence. Next, let's consider how applications evolve over time. And in particular, I want to focus on data structures in our applications. In a traditional client-server application, we modify our schemas on a daily basis, and we handle this using schema migrations. Well, Localfirst applications will evolve in a similar way, and we need a good way of effectively managing or migrating data. And I don't believe anyone has a good solution for this yet, but the Localfirst community is actively working on this problem. It's something we plan on creating tools for in the very near future. Another area in Localfirst applications that needs more work is authorization and authentication. So things work differently with Localfirst because communication could be largely peer-to-peer, and we're going to need different ways of handling auth, but this is an area of active research here at Mycelial, and it's something we plan on addressing in the near future. Now, probably the biggest limitation preventing Localfirst applications from mass adoption today is the fact that CRDTs have just come out of academia, and CRDTs are complicated, and the libraries to hide that complexity and make it easier for you to use just aren't mature as mature as we'd like them to be. But the open source community and our company in particular are working really hard on creating the tools you'll need, and we're making good progress, but things take time. And honestly, we need more early adopters that will work with us on real problems. So as a side note, if you're interested in trying out Localfirst or CRDTs in general, please reach out to us. We would love to connect with you and work with you on solving these challenges. Okay, let's take a look at how you'd use our Young library to create the contacts app we played with earlier. Oh, and by the way, if you're a developer, I've got a hands-on exercise for you in a few minutes. So if you're interested in getting a little bit of hands-on experience, you'll want to pay close attention to what I'm about to talk about so that you can easily finish that exercise. So let me tell you a little bit about our library. The core of our CRDT library is written in Rust, and it's compiled to WebAssembly. And the first platforms we're going to support is the web and Node.js. But with Rust and WebAssembly as a foundation, we've set ourselves up in a way that we'll be able to support potentially many other platforms without having to start from scratch on each one. And not to mention with Rust and WebAssembly, you can expect near native performance. So to use our library, you'll need to install the appropriate NPM dependencies. The first dependency you'll need is the mycelial web or mycelial node, depending on the platform you're using. Next is the mycelial v0 dependency, and lastly is the mycelial WebSocket package. And one quick disclaimer, our libraries are alphas, so at this point you should expect breaking changes and likely a consolidation of these different packages as well. Now, the first thing you'll do after importing the libraries is create an instance, passing in a meaningful namespace. This namespace gets used by things like our relay as effectively a pub sub channel, if you will. Next, to wire up the network adapter that I've talked about a few times, we'll call the WebSocket libraries create function, passing in the instance and a relay endpoint. This is basically all that's necessary to set up data synchronization between your computer and others. Next, you'll create a store by instantiating the store class and passing in the instance. Then to add data to the store, you'll first create an entity by calling entity from, then you'll pass in an entity, unique entity identifier for this entity, and then an object literal that represents whatever the entity is. So in this example, you see a contact. Then after you've created an entity, you'll call the store's add method and pass in the entity, at which point you've stored the contact as a CRDT, and the contact will get replicated to other computers as appropriate. Now, to access the data in our store, there are a few higher order functions that you can use, such as map, filter, reduce, and find. And if you're dealing with the collection, like a list of contacts, you can iterate it with the for loop. Now, there's more to our library than this, but this is enough info to start using it for a simple app like the Contacts app. Okay, I've got a couple of closing comments, and then we'll do question and answers. So first of all, if you're interested in Localfirst and you want to stay in the loop on our open source libraries, please consider joining our mailing list and follow us on Twitter and consider starring and watching our GitHub repos. As I mentioned earlier, we're really interested in getting people using our libraries so we can ideally receive helpful feedback and iterate on these libraries. So if Localfirst and CRDTs are of interest to you, please connect with us and we'd love to hear about your potential use cases. And lastly, I'll reiterate the challenge I gave you earlier. So over the next few days, look at the applications you use and build with Localfirst and CRDTs in mind and ask yourself, would these technologies be helpful and useful in these apps? I think you might be surprised by how many applications could benefit from these technologies. Okay, I've got an exercise for you that should take about 5 or 10 minutes. And in a moment here, I'll paste it in the chat window, which should take you to a set of instructions on how to complete the exercise. But before you start the exercise, I want to give you all a chance to ask myself or our team any questions that you might have. And if you don't have any questions, then I've got a question for you. So with that, I'll open it up to any questions and I'll look at the chat to see if we had any questions along the way.